in the black silence between galaxies, where light has traveled for more than 13 billion years and still has not met a resting place. To faint embers burn. They are not bright enough to dazzle, nor massive enough to command the heavens. Yet they endure small, fragile, ancient, beyond comprehension. Against the ocean of cosmic time, they shine as if they were witnesses to something no other object remembers. Astronomers call them relics, survivors from an era before galaxies spun their first spirals, before planets gathered in the dark, before the chemistry of life was written in the stars. Their light carries an imprint of hydrogen and helium almost untouched by heavier elements. It is the signature of a creation so raw, so close to the beginning, that it seems to emerge not just from the dawn of the universe, but from before the dawn itself. And here lies the paradox. Time, as physics defines it, begins with the Big Bang. Every second, every heartbeat, every orbit of every planet exists because of that moment. Yet these stars whisper of something earlier, a first creation before time, a memory that refuses to fit inside the boundaries of modern cosmology. If such stars truly exist, they are not merely stars. They are fossils of eternity, fragments of a forgotten cosmos embedded within our own. They ask questions that no telescope, no equation, no human mind has yet answered. Was there a universe before ours? Did time itself have a parent? Or do these stars burn as echoes of an infinite cycle, where beginnings and endings are illusions, and creation never truly ends? Their faint glow is not just light from the past. It is a message that the universe may be older, deeper, and stranger than we can yet imagine. For as long as human memory reaches, the night sky has been a canvas of eternity. To ancient eyes, the stars were not silent furnaces of gas, but living symbols, eternal fires that seemed untouched by time's decay. Civilizations carved them into gods and mapped destinies upon their motions. To the Sumerians, they were divine scribes. To the Egyptians, immortal guardians of the dead. To the Greeks, messengers of myth. Each culture looked upward and found eternity staring back, and in that eternity, they sensed origins that stretched before the birth of humankind itself. Stars were not just lights, they were portals into forever, whispers from before time. Yet the veil of mystery began to thin with the arrival of lenses and glass. When Galileo raised his modest telescope to the heavens in 1609, the singular lights of the firmament fractured into revelation. The Milky Way was no painted cloud, but a river of countless suns, each a world unto itself. In that moment, the stars ceased to be eternal gods and became something stranger, physical suns governed by laws, yet still cloaked in mystery. As the centuries turned, the science of the stars deepened. By the early 20th century, astronomers realized stars were not immortal at all. They were born, they burned, and they died, scattering their ashes into space, seeding new generations of stars and worlds. What had once been thought eternal was revealed to be transient, part of a cosmic cycle of birth and death. The stars were alive, but not forever. Then came a new kind of sight, the ability to read the very chemistry of starlight. With stellar spectroscopy, astronomers learned that light was more than brilliance. It was a code. Each star carried within its spectrum a fingerprint of elements, hydrogen, helium, and, in younger stars, the heavier atoms forged in the crucibles of supernova. This discovery unlocked the cosmic genealogy of matter. It revealed that most stars were rich with the debris of earlier generations, proof that the universe was a grand chain of inheritance. But among the billions, a few anomalies emerged. Stars with metallicities so low they seemed untouched by that cosmic recycling. Stars made almost entirely of hydrogen and helium, nearly devoid of heavier elements, as if they had been born before the universe had time to forge its chemistry. These rare objects did not fit the story of stellar generations. They hinted at something more ancient, more elusive. The suspicion grew quietly. At the edges of astronomy, could some stars have been born not merely in the early universe, but before galaxies themselves had formed? Could these dim metal-poor suns be living fossils of the very first creation? If so, their light was not just a remnant of the past. It was a message carried across nearly 14 billion years, from a time when the universe itself was still learning how to shine. The search for origins did not stop with myth or the first telescope. It deepened, as though each generation of humanity felt compelled to peel away one more layer of the heavens. By the late 19th century, scientists had learned to split starlight with prisms and lenses, revealing faint rainbows carved with dark lines. These lines, known as absorption spectra, were more than patterns. They were signatures of atoms. For the first time, humanity could taste the substance of a star without ever touching it. Helium was first discovered not on Earth, but in the sun, its name drawn from Helios, the Greek god of light. The stars were no longer unreachable mysteries, they were knowable. Yet in that knowledge came a paradox. If stars were composed primarily of hydrogen and helium, then why did some shine with evidence of heavier elements? Carbon, oxygen, iron. Where did these come from? This puzzle led to one of the most profound realizations in science. The stars were not passive. They were alchemists, forging the elements of existence within their cores. With each cycle of stellar birth and death, the universe grew richer, seeded with heavier atoms that made planets, oceans, and eventually life. Stars were not eternal, but in their mortality they carried eternity forward, passing creation from one generation to the next. This understanding reshaped astronomy, but it also sharpened the question of antiquity. If stars are born from the ashes of older stars, then the very first stars must have been different, pure, uncontaminated by heavier elements. Scientists called them population 3 stars, a theoretical class that would have blazed into existence soon after the Big Bang. They would have been massive, short-lived, and violent, exploding in supernova that seeded the cosmos with the elements necessary for galaxies, planets, and life. But there was a problem. These stars should have died long ago, leaving behind no direct survivors. If none remained, their existence would only ever be inferred. And yet, hidden among the billions of stars in our galaxy, astronomers began to find faint anomalies, stars whose light revealed almost no trace of metals. Their spectra were nearly pristine, composed almost entirely of hydrogen and helium. They were faint, ancient, and difficult to study, but their chemical fingerprints suggested they were born in the earliest ages of the universe. These stars did not fit comfortably into the categories of known populations. They seemed older than the clusters that held them, older than the galaxies that carried them. Some estimates placed their origins within the first few 100 million years after the Big Bang, an era when the universe was still finding its structure, when galaxies were only beginning to coalesce. The discovery of such stars unsettled the neat timeline of cosmology. If they were as old as their chemistry suggested, then they carried within them a direct memory of creation itself. They were not second-generation stars built from recycled matter. They were primordial, born before the universe had time to enrich itself. To look upon them was to look upon the first fire. These stars also raised a deeper question. How could they survive? Population 3 stars were thought to be immense. burning their fuel in only a few million years before collapsing into black holes or detonating in supernova. The faint, metal-poor stars found in the Milky Way halo were small, quiet, and enduring. Unlike their massive predecessors, they could live for billions of years. This suggested they were not first-generation giants, but perhaps their immediate descendants, born in the aftermath of the first supernova, when the universe was still in its infancy. Their chemistry was nearly primordial, their lifespans long enough to survive into the present. They were fossils not of the first spark itself, but of the first echoes. To early astronomers, this was nothing short of revelation. Here were objects that had persisted across nearly the entire history of the cosmos, still burning when stars, galaxies, and even planets had come and gone. They were windows into a past so distant it seemed almost outside of time. Studying them promised not only to illuminate the origins of the universe, but also to test the limits of cosmological models themselves. But with that promise came unease. Some of these stars, when dated through careful modeling of their nuclear processes, appeared to be older than the universe itself, at least older than the 13.8 billion year age inferred from cosmic microwave background measurements. This was, of course, impossible, at least within standard cosmology. The contradiction revealed not that the stars had literally existed before time, but that our measurements and models were imperfect. Either the methods used to estimate stellar ages carried errors, or the cosmological timeline itself required refinement. This tension between observation and theory marked the beginning of a scientific mystery that continues to this day. Were these anomalies simple errors of calibration, or were they pointing towards something deeper, a gap in our understanding of how the universe began and how time itself is measured? The earliest astronomers to confront this puzzle could scarcely have imagined its implications. They had gone from seeing stars as gods to suns to furnaces, and finally to fossils of creation. Each stage of discovery deepened the paradox rather than resolving it. For in chasing the origins of stars, humanity had stumbled upon something larger, the origins of time itself. The suspicion grew stronger as the 20th century unfolded. With each new telescope, with each new survey of the sky, astronomers found more of these faint, metal-poor stars lurking in the halo of the Milky Way, drifting relics from a forgotten era. They were like ancient wanderers, orbiting quietly beyond the galactic disk, untouched by the violence of younger stars. Their persistence suggested that the universe was littered with memories, hidden in plain sight, and so a question emerged that remains unanswered. Could some of these stars truly be older than the structures around them? Could they, in some sense, be survivors from a creation before creation, a cycle of the cosmos that preceded our own? If so, their light would not only trace back to the Big Bang, but perhaps to something before it, something that science has only begun to imagine. The origins of the discovery were humble, a telescope, a prism, a spectrum of light. Yet the implications are profound. By dissecting faint rays from distant stars, humanity unlocked a story that stretches beyond galaxies, beyond time, and perhaps beyond the singular universe itself. The stars were no longer just beacons of the present. They had become fossils of eternity, carrying secrets not only of what came after the beginning, but of what might have existed before it. The first hints of impossibility rarely arrive as thunder. They whisper instead, faintly, like static carried across a wire. When astronomers began to announce the existence of stars whose chemistry suggested an age brushing against, or even surpassing, the universe itself, the scientific community did not erupt in celebration. It hesitated. For if these claims were true, They would not merely adjust the margins of astronomy, they would tear at its foundation. Skepticism was inevitable. To suggest that a star could predate its host galaxy, or that an object might carry within it the ashes of a time before time, struck at the heart of cosmology's fragile coherence. The Big Bang was not only a model, it was a boundary. It marked the beginning of expansion, the moment when energy condensed into matter, when light first separated from darkness. To place something before it was to invite a contradiction, a paradox. And science is built upon the careful avoidance of paradox. The language of the debate soon centered on the idea of population. 3 stars, a term whispered in lecture halls and embedded in the margins of early journals. They were imagined as the firstborn suns, igniting just a few 100 million years after the Big Bang, composed of nothing more than hydrogen and helium, untainted by heavier elements. They would have been immense, unstable, and ephemeral, living fast and dying young, scattering their enriched remains into the void. None, by theory, should have survived. To find one intact would be like stumbling upon a living ember from a fire that should have burned out eons ago. But some observations seemed to suggest otherwise. Stars, with vanishingly low metallicity, as close to pristine as physics allowed, had been catalogued in the halo of the Milky Way. Their compositions told a story written in light. No carbon, no iron, no oxygen, nothing but the simplest ingredients of creation. To many, these objects were fossils, if not of the first generation, then perhaps of their immediate descendants. Their survival challenged the assumption that the universe's earliest actors had long since vanished. Einstein's relativity loomed over these discussions like a silent judge. Relativity taught that space and time were not infinite backdrops, but a single, malleable fabric born together in the moment of creation. To suggest that something existed before was not only unscientific, it was nonsensical. Before the Big Bang, there was no before, no ticking clock, no stage on which matter might stand. If these stars were older than the accepted age of the cosmos, then the flaw lay not in time itself, but in human measurement, in the frailties of equations applied to nuclear reactions and cooling rates. Yet unease lingered. What if the contradiction was not a mere error? What if it pointed towards something deeper, a hidden dimension of cosmology that had not yet been grasped? If stars truly carried within them the memory of a time unrecorded, then the universe's story was not linear, not singular. It was layered, cyclical, or branching in ways no telescope had yet revealed. This tension haunted the early search. Astronomers scoured the galactic halo, trawling for the dimmest, most ancient suns, while theorists sharpened their models, testing every variable, recalibrating every constant. Each discovery of an ultra-metal poor star was greeted with both wonder and suspicion. Were these relics genuine fossils of cosmic dawn, or statistical anomalies misread through human error? Philosophers of science observed from the edges, noting that the controversy struck at something more than physics. It struck at the narrative itself. Humanity has always sought beginnings, the first day, the first light, the first breath. If the universe itself could not provide a singular starting point, then what did that mean for the story we tell about existence? Was the Big Bang a genesis, or merely one chapter in a cycle of countless unseen creations? The debates did not resolve quickly. They deepened, as though each new discovery only widened the rift between theory and observation. And in that widening rift, a quiet unease spread, the suspicion that the universe might be stranger than even Einstein had allowed, that the fabric of time might contain folds, scars, or memories of worlds that burned before our own. The search for truth in the heavens always begins with faint signals. For astronomers of the late 20th century, those signals were etched not in images of spirals or clusters, but in the fragile fingerprints of starlight. Spectroscopy, the art of dividing light into its hidden spectrum, revealed more than beauty. It revealed ancestry. A star's rainbow, when stretched thin across a detector, carried within it the secrets of its birth, the elements forged in its core, the relics of ancient supernova that once seeded its nursery. It was within these spectral lines that whispers of impossibility were first heard in the galactic halo, that vast, dim sphere of stars encasing the Milky Way. Astronomers found suns whose metallicity was not merely low, but nearly absent. In astronomical language, metals are everything heavier than helium. Stars like the sun are rich in them, brimming with carbon, oxygen, iron, and countless other atoms forged in previous generations. But these halo stars seemed stripped bare. Their light carried only the simplest of patterns, as though the recipe for their birth had been written in the most primitive ink of the cosmos. The first great shock came with the discovery of a star catalogued as HD 140, later nicknamed the Methuselah star. Its spectrum suggested an age of more than 14 billion years older, by some calculations, than the universe itself. Astronomers knew this could not be true. The paradox was immediately attributed to uncertainties in stellar models: how quickly hydrogen is consumed, how convection stirs a star's core, how opacity shifts as fusion proceeds. Yet the unease remained. How could the data place a star beyond the edge of time? Others followed. He won 3-7, a star with iron content less than 100,000th that of the Sun, discovered in 2005, then SMS SJ03, another with practically no detectable iron at all. These stars were not bright beacons, but dim, fading embers, buried deep in the halo, seen only by the most patient surveys. To the untrained eye, they appeared unremarkable, but their chemistry told a different story, one of unimaginable antiquity. The community split along lines of interpretation. Some argued these were not population 3 stars themselves, but the next generation, born from the ashes of the very first explosions. If the firstborn giants had lived for only a few million years before collapsing into black holes or tearing themselves apart, their remains would have enriched the primordial hydrogen just enough to seed this second wave. By this reasoning, the ultrametal-poor stars we see today are fossils not of the first fire, but of its immediate aftermath, witnesses rather than originators. Yet, even this view carried implications almost too vast to hold. If these stars indeed trace their lineage to the very dawn of structure, they are older than the Milky Way itself, drifting through space long before the galaxy's spiral arms unfurled. They are not children of the Milky Way, but its ancestors gathered into its halo only later, when gravity swept them into its growing embrace. In a sense, the Milky Way did not give birth to them, they gave birth to the Milky Way. Einstein's shadow lingered here too. The paradox of before remained unresolved. The stars did not exist outside of time, but they hinted at epochs just beyond the reach of human imagination. If the Big Bang was the first instant of creation, then these stars formed perilously close to its horizon, as though they carried the very memory of the universe's awakening. The language of before crept back into scientific discussion, not as literal truth, but as metaphor, a way of expressing the sense that these objects belonged to a realm earlier than history, earlier than galaxies, earlier than the world we know. the skepticism persisted. Could these stars be misclassified? Could their spectra be misleading, contaminated by intervening dust or by unknown processes in their atmospheres? Stellar physics is a labyrinth filled with uncertainties in convection, turbulence, and opacity. A slight error in modeling could shift a star's apparent age by billions of years. Some insisted that this was all the puzzle amounted to, an accounting mistake. Yet the number of discoveries grew, and with each one, the possibility of coincidence shrank. Surveys like the Hamburg ESO program, the Sloan Digital Sky Survey, and later the Sky Mapper project devoted themselves to scouring the heavens for such relics. The work was slow, painstaking, requiring sifting through millions of candidates to find a single star with the right spectral scars. But every success deepened the unease. Each ultra-metal poor star was another voice from the cosmos, whispering that the story of time may not be as straightforward as textbooks had promised. The philosophical consequences hovered at the edges of these discussions like ghosts. If stars could be older than galaxies, if they could carry within them the chemistry of creation itself, then perhaps the universe was not a clean line from beginning to end, but a palimpsest, a manuscript written, erased, and written again. Some cosmologists speculated quietly. Could these stars be remnants not only of the Big Bang, but of cycles before it? Could they be scars of a universe that once collapsed only to ignite again? Even to ask such questions was dangerous, for they risked blurring the line between science and speculation. Yet the very existence of these relics forced the boundary to shift. Science, after all, is not static. It evolves in response to the evidence, however faint or contradictory, and in the faintest light of the oldest stars, evidence was mounting that the cosmos may hold secrets too vast to be contained by a single narrative of origin. In this fragile tension, the early years of the debate unfolded, a dance between data and doubt, between the rigor of physics and the daring of imagination. What began as whispers in spectral lines became an ongoing challenge to cosmology itself. The Methuselah star, the halo fossils, the whispers of population 3, each was a question posed to the universe. And the universe, in its silence, offered only more mystery beneath the restless atmosphere of Earth, where stars tremble and blur in the turbulence of air. The first serious searches for the oldest suns began. The astronomers of the mid-20th century worked with instruments far less powerful than those that would come later. Yet their ambition was boundless. With glass lenses, mirrors, and photographic plates, they tried to capture the faint light of stars so ancient their photons had wandered for billions of years before touching human eyes. They searched not in the bright arms of the Milky Way, where new stars are born in clouds of gas and dust, but in its halo, the vast, ghostly sphere of stars surrounding the galaxy like a shell. The halo was quiet, barren, and dim. It was here that astronomers hoped to find what the younger, crowded disk could not provide: relics untouched by the cycles of birth and death, fossils of an earlier age. The method was simple in principle, yet demanding in practice. Light from each star was split into its spectrum, revealing a barcode of dark lines where atoms in the stellar atmosphere absorb specific frequencies. Each line was a clue: hydrogen leaving its imprint, helium marking its presence, carbon and iron showing the handiwork of earlier stars. The absence of these heavier elements was not just silence, it was a profound statement. A star made only of hydrogen and helium was as close as physics could bring humanity to the original matter of the cosmos. In the 1950s and 1960s, as spectroscopy matured a startling pattern emerged. Some stars carried vanishingly small amounts of metals. Their compositions were almost pristine, almost primordial. They became known as ultra-metal-poor stars, their chemical signatures echoing a universe unmarked by the heavy elements forged in stellar furnaces. To those who read these spectra, it was as though the DNA of the universe had been laid bare, strands of light spelling out the conditions of creation itself. But the work was fraught with difficulty. Stellar models were riddled with uncertainties: how fast hydrogen was consumed, how convection stirred material from core to surface, how fusion reactions unfolded in dense, turbulent interiors. A slight miscalculation could alter the estimated age of a star by billions of years. Instruments, too, strained at their limits. Observations were blurred by the shifting sky, by faintness, by the sheer difficulty of isolating a dim, ancient star from the ocean of light around it. And yet, again and again, the data returned with whispers of impossibility. Stars like HD 140,283, later called the Methuselah star, appeared to be older than the universe itself. Not just ancient, but impossibly so, with age estimates brushing against 14.5 billion years, while the universe was calculated to be only 13.8. The contradiction unsettled even the most cautious astronomers. Either the methods were flawed, or the understanding of time itself was incomplete. For the first time, the notion that stars could serve as clocks of creation began to feel precarious. If their light was telling the truth, then the neat boundaries of cosmology were in question. Could there truly be objects that carried within them a memory of a time unaccounted for, a moment outside the narrative of the Big Bang? Or was the paradox itself the message that the universe, in its earliest instance, is a mystery still beyond human grasp? The early investigations did not resolve these questions. They only sharpened them. With every ultrametal-poor star catalogued, with every spectrum that revealed the stark absence of metals, the stakes grew higher. These faint suns seemed to speak in riddles, stars that should not exist, shining in defiance of cosmological order. They burned quietly in the galactic halo, not as ordinary points of light, but as potential witnesses to a creation deeper and older than time itself. The pursuit of these ancient suns unfolded slowly, like a long exposure photograph gathering light one photon at a time. In the 1960s and 1970s, the field of stellar archaeology began to take shape. Astronomers realized that the halo of the Milky Way was not just a sparsely populated outer shell, but a kind of archive. Unlike the disk, where new stars constantly recycled the ashes of old ones, the halo preserved a record of the galaxy's earliest epochs. It was here, in these lonely regions, that relics of cosmic youth might survive untouched. But the search was demanding. The stars they sought were faint, often thousands of light years away, scattered like dust against the black canvas of space. Finding them was like sifting grains of sand across endless shores, hoping to stumble upon one made of glass. Wide-field surveys became the first step, identifying candidates by their colors and brightness. Only then could the precious hours of large telescopes be devoted to splitting their light into spectra, revealing whether their chemical signatures matched the profile of extreme antiquity. Among the earliest discoveries was the striking realization that not all stars were chemically alike. Some burned with the richness of iron and carbon, their atmospheres infused with the debris of countless stellar generations, but a rare few were stripped bare of such history. Their light betrayed almost no trace of metals, as though they had condensed directly from the untouched gas that flowed from the Big Bang itself. These were not ordinary stars. They were outliers, anomalies, puzzles waiting to be solved. The metaphor of DNA grew stronger during these years, just as the genome of a living being encodes its ancestry. The chemical composition of a star encodes the conditions of its birth. Heavy elements are like mutations, accumulated as generations pass. The absence of those mutations, the sheer purity of hydrogen and helium, suggested an origin unimaginably close to the moment when the universe first cooled enough for atoms to form. To hold such light in a spectrograph was to hold, in some sense, the memory of creation itself, yet this memory was never easy to interpret. Stellar physics brims with uncertainties, and the interior of a star cannot be directly observed. Instead, astronomers relied on models, vast calculations of fusion rates, opacities, convection currents, and the delicate balances that determine how long a star of a given mass can burn. A minor adjustment to any of these variables could alter the star's estimated age by hundreds of millions of years. And so when objects like HD 140,283 appeared to defy the age of the universe, astronomers were torn between awe and caution. Was the star truly older than the cosmos, or was it the models that were incomplete? The Methuselah star became a touchstone of this debate. Its calculated age hovered uncomfortably close to 14.5 billion years, while the most precise measurements of the cosmic microwave background placed the universe at 13.8. That difference, though small in cosmic terms, was devastating in principle. A star cannot outlive the universe that contains it. To reconcile the paradox, astronomers considered every possibility: refinements in nuclear reaction rates, corrections in parallax measurements of distance, adjustments in the physics of stellar atmospheres. Each refinement brought the estimated age closer to compatibility, yet never quite erased the shadow of the question: how could such a contradiction arise at all? Other discoveries followed, each one layering new complexity onto the mystery. He, 01, a star with less than 1/200,000th the Sun's iron content, shocked the community in 2002. Its spectrum was almost featureless, a canvas unmarked by the brushstrokes of stellar evolution. Then came He 13, even poorer in metals, and later SMSS, whose iron content was so low it could not be measured at all. Each of these stars seemed to push the frontier of possibility further back, closer to the first fires that lit the darkness after the Big Bang. These early investigations revealed more than stars. They revealed the fragility of human narratives. For centuries, the cosmos had been imagined as a story with a beginning, middle, and end. The Big Bang served as a firm prologue, a single point from which all else flowed. But the ultra-metal-poor stars blurred that simplicity. They suggested a universe not of clean beginnings, but of echoes, survivals, and traces. A universe that resists being pinned to a single origin, instead unfolding like a palimpsest, with each new layer written upon the faint remains of the last. The astronomers of the mid-century could not resolve these contradictions. Their instruments, limited by atmosphere and technology, offered only glimpses of the truth, and yet those glimpses were enough to ignite a growing unease. It was not only a scientific unease, but a philosophical one. For if the stars themselves seemed older than the universe, then perhaps the very definition of beginning was flawed. Perhaps time itself was more intricate than a single arrow shot from a single bow. As larger telescopes came online, the 100-inch Hooker telescope at Mount Wilson, the 200-inch Hale telescope at Palomar, and later the Keck observatories in Hawaii, the search grew sharper, the spectra clearer. Each new observation brought the paradox into sharper focus. The universe tells a story of origins, but in the faint glow of its oldest stars, that story seems to stumble over its own first word. The early investigations did not answer the mystery. Instead, they framed it. They established the problem that would haunt cosmology for decades to come, that within the Milky Way itself, in the halo above our heads, there exist suns so old, so pure, and so improbable, that they seem to belong not just to our universe, but to something before it. Was not until humanity lifted its eyes above the blur of its own atmosphere that the ancient whispers of the stars began to grow sharper. The launch of the Hubble Space Telescope in 1990 marked a turning point, a new lens above the trembling air, where photons could arrive unscattered, carrying the truth of ages across the void. With Hubble, the sky unfolded in a clarity never before seen, its instruments tracing the faint signatures of stellar populations older than galaxies themselves. But even as Hubble revealed distant galaxies forming less than 1 billion years after the Big Bang, the riddle of impossibly old stars closer to home deepened. Among them was one that would become legendary, HD 140,283, known to astronomers simply as the Methuselah star. Its light, studied with unprecedented precision, told a story of age beyond imagination. Stellar models, parallax measurements, and nuclear reaction rates converged on a figure unsettling in its implication: 14.5 billion years. Older, in some calculations, than the universe itself. Astronomers refined their methods, correcting for opacity, convection, and uncertainties in nuclear fusion chains. The paradox softened. The star was likely closer to 13.7 billion years. But the impression lingered. Here, only 200 light-years from Earth, was an ember that seemed to have watched the universe ignite. The very fact that it could rival the cosmos in age made it an icon of mystery, a reminder that not even the nearest stars could be fully explained. As ground-based technology advanced, massive observatories with mirrors spanning 8 and 10 meters pushed the frontier further. Keck in Hawaii, the Very Large Telescope in Chile, and the Subaru Telescope on Mauna Kea turned their gaze to the galactic halo. Their surveys, patient and relentless, found stars whose metallicities were so close to zero they defied categorization. He 1327 to 2326, discovered in 2005, carried less iron than 100,000th of the Sun, its spectrum nearly blank. Later, SMS SJ031 300.366 670,839.3 revealed iron so scarce it could not be measured at all. These were not ordinary stars. They were fossils, their light carrying the untouched chemistry of creation. Spectroscopic surveys grew into a new kind of archaeology. The Hamburg ESO program, Sloan Digital Sky Survey, and Australia's SkyMapper project swept the heavens, searching through millions of stars to find the few precious relics. Each new discovery seemed to edge closer to the mythical population 3 stars, the first generation born after the Big Bang, composed only of hydrogen and helium. None had yet been found in the flesh, but their descendants, faint and nearly pure, shimmered at the edges of the Milky Way like messages in a forgotten script. And then came James Webb, in the deep infrared. Webb pierced further than any eye before it, reaching galaxies less than 200 million years after the Big Bang. Its mirrors reflected not just light, but time itself, stretching back to an era when the first stars must have burned. Within these infant galaxies, the fingerprints of primordial stars, may yet be detected, their brilliance overwhelming, their lifespans short, their deaths catastrophic. Webb revealed galaxies forming far earlier than models had predicted, their light already ancient when the Milky Way was still only dust. But even in these breakthroughs, anomalies persisted. Some globular clusters, vast spherical swarms of stars older than the Milky Way, showed chemical signatures that resisted explanation. Their populations seemed too uniform, too ancient, as though they had emerged fully formed, carrying within them the residue of a creation that should have been erased. If these clusters were younger than the universe, they wore their youth with uncanny resemblance to a time before time. The idea crystallized slowly, reluctantly. Perhaps, among the trillions of stars scattered across the observable universe, a rare few were true relics of the first ignition. They were not ordinary suns, nor even ordinary fossils. They were the survivors of a creation before creation, still burning against all odds. If such stars could be confirmed, they would not merely rewrite the history of astronomy, they would challenge the very notion of beginnings. The telescopes had given humanity vision sharper than ever before. Yet in that clarity, the mystery only deepened. The oldest stars did not surrender their secrets easily. Instead, they gleamed faintly at the edges of knowledge, hinting at truths both wondrous and unsettling, that perhaps the universe is older, stranger, and more infinite than the story told so far. The James Webb Space Telescope, poised at the quiet balance point of Lagrange 2, began sending back images that seemed almost impossible. Galaxies appeared where there should have been none, vast collections of stars shining less than 300 million years after the Big Bang. Their light had traveled for more than 13 billion years, carrying within its spectrum the chemical fingerprints of stars that had already lived and died before these galaxies took form. For astronomers, it was a revelation and a shock. Standard cosmological models had predicted that the universe in that early epoch should have been dark, dominated by hydrogen clouds, yet untouched by fusion. Instead, Webb's mirrors revealed a cosmos that seemed hurried, restless, already alight with stellar furnaces when theory insisted it should have only just begun. Among the most profound questions was whether Webb had finally brushed against the long-sought population 3 stars, the very first generation born in a universe of pure hydrogen and helium. These stars were expected to be enormous, some hundreds of times the mass of the Sun, burning with blinding intensity and living only a few million years before collapsing in supernova that seeded the cosmos with heavier elements. They were ghosts, theoretical and unobserved, yet their existence was essential. Without them, the chemical richness of later galaxies, planets, and life itself could not be explained. Webb could not resolve single stars at such distances, but its instruments could detect the collective glow of primordial populations. In faint galaxies with surprisingly bright ultraviolet light, some astronomers believed they were seeing the indirect traces of those first suns. Closer to home, the mystery deepened in the halo of the Milky Way. Surveys using instruments like Gaia, coupled with ground-based spectrographs, mapped the orbits and compositions of thousands of ancient stars. Patterns emerged, clusters of metal-poor stars moving together, as if remnants of smaller galaxies cannibalized by the Milky Way billions of years ago. Within those populations, a few individuals stood out as singularly pristine, their spectra showing almost no trace of metals at all. These were not merely old stars. They were living fossils, possible descendants of the very first wave of stellar creation. Their presence whispered that fragments of the earliest universe still circled quietly around the modern one. unnoticed until the right instruments were aimed in their direction. The Methuselah star remained a haunting figure throughout these debates. Astronomers refined its age again and again, its uncertainty shrinking as models improved, but always it hovered at the edge of the universe's own timeline. Was it an outlier in calculation, or a genuine clue that time itself might stretch further back than currently believed? The philosophical implications were heavy. If a single star could be older than the universe, then either the models of cosmic expansion required revision, or the definitions of time and beginning were more fragile than once thought. Some theorists turned to exotic ideas. Could the universe have experienced more than one creation? Cyclic cosmologies, long pushed to the fringes, gained renewed attention. Perhaps the Big Bang was not the ultimate beginning, but one in a series of expansions, each leaving behind traces in the form of anomalous stars. Others considered the possibility of unknown physics in stellar evolution, processes in nuclear fusion that could extend the apparent lifetimes of stars without actually contradicting the universe's age. Still, none of these speculations erased the unease of finding stars that seemed to stretch against the limits of known time. Globular clusters offered yet another puzzle. These dense, spherical congregations contained hundreds of thousands of stars, many of them as old as the Milky Way itself. Their chemistry often revealed remarkable uniformity, as though their stars had formed all at once from a single primordial cloud. But within some clusters, astronomers found multiple generations, populations that should not have coexisted, according to simple models. The question arose, had these clusters been seeded by the deaths of population 3 stars, gathering the enriched remains into new formations? Or had they somehow emerged from conditions that preserved the chemistry of the earliest epoch, blurring the boundary between first creation and what followed? Every observation seemed to balance between revelation and uncertainty. The sharper the instruments, the deeper the paradox grew. Webb, Hubble, Keck, and the VLT together painted a portrait of a universe rushing into maturity faster than anticipated, as though creation itself had not unfolded linearly, but in bursts of brilliance and silence. What was once assumed to be a gradual dawn now appeared more like a lightning storm, flashes of light illuminating the cosmos before the darkness had fully receded. The pursuit of the older stars became something more than astronomy. It became philosophy cast in data and light. To look at HD 140,283 or at iron-free halo stars was to gaze not simply at matter, but at time itself compressed into fire. The question was no longer whether such stars existed, but what their existence meant. Were they survivors of the first generation? Were they messengers from a cycle before our own? Or were they evidence that the story of the cosmos, its beginning, its growth, its future, was far stranger than linear expansion and simple birth? The universe, in its silence, offered no easy answer. The stars burned as they always had, indifferent to the timelines constructed around them, and yet, through their light, humanity glimpsed the faint suggestion of another truth, that beginnings may not be singular, that creation may not be bound to one instant, and that hidden among the galaxies and the void, the rarest of stars may carry within them the memory of more than one universe. In the great ledger of the cosmos, where light is the ink and time the parchment, contradictions have begun to appear. Astronomers, armed with telescopes that peer across gulfs of billions of years, have uncovered stars whose ages seem to trespass beyond the accepted bounds of creation itself. The universe, as measured by the expansion of galaxies and the faint afterglow of the Big Bang, is estimated at 13.8 billion years. Yet a handful of stars, when their chemistry and evolution are traced with the precision of modern astrophysics, whisper of lifespans that edge against, and in some calculations, even exceed that number. The Methuselah star stands as the most famous of these enigmas. Its spectral fingerprints, etched in the faint light that reaches Earth, suggest an age of 14.5 billion years older than the cosmos it inhabits. Refinements in measurement pull the value back toward the edge of possibility, yet never comfortably within it. It exists like a riddle scrawled across the sky, a reminder that the equations humans have written to describe time and matter may not yet capture the full truth. The tension lies between two great disciplines. Cosmology, built upon the expansion of space and the relic light of the cosmic microwave background, offers a universe finite in age, with a clear beginning. Stellar astrophysics, by contrast, measures the rhythms of fusion, opacity, and chemical evolution within stars themselves. When these two chronologies clash, one must yield. But which is an error, the grand scale of the cosmos, or the intimate physics of stellar interiors? Some scientists point to the models of stellar structure, suggesting that hidden complexities may extend the apparent lifetimes of certain stars. Uncertainties in nuclear reaction rates, in the diffusion of elements through stellar atmospheres, or in the calibration of distances could all conspire to shift the numbers. Others look instead to cosmology itself, to the assumption that the universe's clock began in a single instant. Speculative theories rise in the gaps left by contradiction. In cyclic cosmologies, the universe does not begin once, but endlessly, reborn through collapses and expansions that stretch beyond human conception. In eternal inflation, vast regions of space perpetually sprout new universes, each with its own beginning, while others continue to age into eternity. Within these frameworks, the presence of a star older than its universe need not be paradoxical. It could be a survivor, a relic carried across the seam between creations. These possibilities, though far from proven, press against the boundary of science and philosophy. If time itself is not absolute, if beginnings are local rather than universal, then the meaning of age becomes more fluid. A star that seems older than the universe may not be an error. It may instead be a witness to a larger cycle of reality, one in which the Big Bang was not the first ignition, but merely the most recent dot. And yet, data resists easy dismissal. Each new observation of metal-poor stars, each survey of the galactic halo, brings forth candidates that challenge the standard timeline. They are few, scattered like whispers in the dark, but they persist. To ignore them would be to discard clues that may point toward a deeper understanding of existence. Itself, in these contradictions lies a profound lesson. The stars are not merely objects of fusion and gravity. They are paradoxes in plain sight, written across the heavens as both beacons of physical law and hints of truths not yet known. They illuminate not only the space around them, but also the limits of human comprehension. The mystery deepens, not because answers recede, but because each discovery opens wider the chasm of possibility. Are these stars mismeasured anomalies, or the first solid evidence that reality is vast, older, and more intricate than the story told by 13.8 billion years? The silence of the night sky offers no reply. Yet in that silence, the questions grow louder, pulling science closer to the edge of what it dares to imagine. The paradox of stars older than the universe did not fade with time. It grew sharper, more unsettling, as each new attempt at resolution produced only further questions. The Methuselah star became a touchstone of this tension. its age estimates drifting with every refinement, yet never dissolving into comfort. With improved parallax data from the Hubble Space Telescope and later Gaia, the star's age narrowed to a range that brushed uncomfortably close to the cosmic limit. But even within margins of error, the unease lingered. A universe defined by precision minus 13.8 billion years does not easily coexist with stellar lifespans that extend to the very threshold of that boundary. The discrepancy was not merely technical, it was philosophical, striking at the nature of beginnings themselves. The question haunted cosmology. What if the problem did not lie in the stars, but in the story of the cosmos? The Big Bang, once considered an absolute beginning, has always carried within it a profound mystery. The equations of general relativity, when run backward, collapse into a singularity, a point where density, temperature, and the very fabric of time itself reach infinity. Yet physicists have long known that such infinities are warnings, not truths. They signaled the breakdown of theory, not the true nature of reality. If the singularity is not the beginning, then perhaps the universe's clock does not start at zero. Perhaps what humans call the Big Bang was only a transformation, a boundary between one era of existence and the next. Into this space of doubt flowed bold ideas. Roger Penrose's conformal cyclic cosmology envisioned a cosmos that endlessly renewed itself. In his theory, the death of one universe, stretched thin and emptied of matter, becomes mathematically indistinguishable from the fiery birth of another. Across these eons, relics could persist, not galaxies or planets, but radiation, gravitational echoes, or perhaps even stars lingering on the seam between cycles. The idea that a star might predate this universe finds, if not proof, at least a conceptual home here. Yet even without invoking other universes, the paradox remains powerful within this one. Stars themselves are imperfect clocks. Their lives depend on countless variables: initial mass, chemical composition, the dynamics of convection deep within their interiors. A star with almost no metals, like the ultrametal poor stars observed in the halo, burns its fuel differently than a younger, metal-rich star like the Sun. Hydrogen and helium fuse more slowly when the star lacks the heavy elements that normally act as catalysts. These ancient suns are miserly with their energy, stretching lifespans to cosmic extremes. What appears at first as an impossibility may in fact be testimony to their remarkable efficiency. Still, the numbers press against the limits. HD 140, with its surface rich in hydrogen and nearly devoid of heavier elements, is estimated at 14 billion years, with uncertainties that barely leave breathing room for the universe itself. If such margins prove reliable, then cosmology must bend. The cosmic microwave background, the faint echo of the Big Bang, is one of the most precise measures of the universe's age. Yet even there, tensions exist. Observations of distant galaxies and the rate of cosmic expansion, known as the Hubble constant, reveal discrepancies depending on the method used. One clock says the universe is older, another insists it is younger. Into this discord, the stars add their stubborn voice, insisting that the cosmos may not be so neatly measured. The unease grows deeper when considering time itself. Time is not a backdrop against which events unfold. It is part of the fabric woven with space, as Einstein revealed. If space-time has a beginning, then to ask what came before is to misunderstand the question. Yet the existence of stars whose ages seem to extend beyond that beginning suggests a paradox, not of misunderstanding, but of incompleteness. Perhaps time did not simply begin, but emerged from something more fundamental. Perhaps these stars are not truly older than the universe, but are markers pointing toward the deeper foundations from which both stars and time arise. For the astronomers who measure these anomalies, the stars become both a problem and poetry. They are outliers, statistical thorns in carefully woven models, but they are also lighthouses on the edge of understanding, shining in defiance of the neat equations that would contain them. They remind humanity that the universe is not obliged to conform to human expectation. Its truths are stranger, wilder, more ancient than the models suggest. In the galactic halo, these paradoxical suns drift silently, bound by gravity, yet untethered from human certainty. They burn slowly, stubbornly, as though guarding secrets not yet ready to be told. Each photon they release carries not only the story of nuclear fusion, but the echo of time itself, time measured not in human years or cosmic ages, but in the persistence of mystery. Thus, the deeper the investigations reach, the deeper the mystery becomes. What seemed like an error in calculation begins to resemble a window into something profound. The possibility that the universe humans inhabit is not the first, nor will it be the last. The stars older than the universe may not merely be anomalies. They may be messages, written in light, from a creation that transcends beginnings. At the frontier, where certainty fades into speculation, the search for the oldest stars presses against the extreme edge of science. The paradox of suns that seem older than the universe has forced astronomers to widen their gaze, to consider forces and materials invisible to the eye, and to explore models of reality that stretch beyond the familiar fabric of space-time itself. Here, in the borderlands of knowledge, the most ancient stars may no longer be ordinary beacons of hydrogen and helium. They may be something stranger, hybrid creations shaped by the hidden scaffolding of the cosmos, dark matter. The unseen mass that outweighs ordinary matter 5-1 may hold the key to the enigma. Though invisible, it shapes galaxies, guiding their formation with its silent gravity. In the earliest moments of the universe, before galaxies coalesced, clouds of gas may have collapsed under the pull of dark matter, igniting the very first stars. Some theoretical models suggest these primordial suns were unlike anything seen today, dark stars, vast and luminous, their heat fueled not solely by nuclear fusion, but by the annihilation of dark matter particles within their cores. If such exotic stars ever lived, they may have burned more slowly, lasting longer than physics once believed possible. Their descendants, or the fragments of their ashes, might still drift in the galactic halo, ghosts from a chapter of creation humanity has barely begun to imagine. Beyond dark matter lies the even, stranger terrain of quantum cosmology. The equations of general relativity point backward to a singularity, but quantum mechanics resists such absolutes. Some interpretations suggest that time did not begin in a single flash, but emerged gradually from a more fundamental state, a sea of quantum fluctuations, without before or after. If time itself has no true beginning, then the paradox of ancient stars is transformed. They need not fit within the neat confines of 13.8 billion years, because the cosmos itself may be older, deeper, layered with errors that reach beyond measurement. The cosmic microwave background, the faint afterglow of the Big Bang, seems at first to argue against such speculation. It is the most ancient light known, a frozen snapshot of the universe, just 380,000 years after its birth. Yet even this relic, mapped with exquisite precision by satellites like WMAP and Planck, carries anomalies, faint cold spots, unexplained asymmetries, patterns that some scientists believe may be scars from a reality older than our own. If the microwave background is the echo of a single creation, then it is the limit of time. But if it bears the imprint of something earlier, collisions between universes, traces of cycles before this one, then the stars in question may indeed be bridges, shining across the seam between worlds. To test such ideas requires instruments that strain the limits of human ingenuity. The James Webb Space Telescope now peers deeper into the early universe than ever before, uncovering galaxies that formed astonishingly quickly, their starlight blazing less than 300 million years after the Big Bang. On Earth, massive surveys like Apogee and Lamost sift through millions of stars, searching for chemical fingerprints so rare they may trace directly to the dawn of creation. Detectors buried deep underground hunt for dark matter, hoping to confirm the existence of particles that could explain the endurance of exotic stars, and yet, for all the progress, the truth remains elusive. The oldest stars shine faintly, hidden in the galactic halo or buried in globular clusters, their light barely distinguishable from the countless suns around them. They are riddles written in photons, puzzles whose answers lie at the edge of science itself. The search for them is not merely about cataloging anomalies. It is about confronting the possibility that the universe is larger than the story told so far, that what appears impossible may, in fact, be the first glimpse of a deeper order. The extreme edge of science is not a place of answers, but of questions sharpened to their finest point. Here, dark matter, quantum time, and ancient starlight converge into a mystery that resists every attempt at closure. Perhaps these stars are not contradictions, but invitations, bridges across cycles, signposts pointing beyond the horizon of the known, at the farthest reaches of knowledge. Science begins to resemble poetry written in equations. The quest to explain stars that appear older than the universe draws researchers into a domain where the boundaries of physics blur, where every discovery deepens the shadows rather than dissolves them. It is here, in this liminal space, that dark matter, quantum time, and ancient starlight weave together into a single, unresolved tapestry. Dark matter remains the most compelling suspect in the riddle. Though never seen directly, its gravitational fingerprint is undeniable. Galaxies spin too fast for their visible stars to hold together. Galaxy clusters bend light from more distant galaxies in ways only hidden mass can explain. Without dark matter, the large-scale structure of the universe, firmaments, voids, and webs stretching across billions of light-years, could not exist. If it sculpts galaxies, then surely it also sculpted the first stars. Some scientists have suggested that the earliest stars were not powered only by fusion, but by the annihilation of dark matter particles themselves. These hypothetical dark stars would have been colossal, far larger than the Sun, with cores suffused by energy not from hydrogen burning, but from the invisible collisions of weakly interacting massive particles. Unlike ordinary stars, they could have endured for astonishing timescales, outlasting the expectations of traditional models. Their remnants, if they exist, might still flicker faintly in the halo of the Milky Way. If one of today's ultra-metal-poor stars is a descendant of such an exotic ancestor, its extraordinary longevity might explain the paradox. But dark matter is not the only frontier shaping this mystery. At an even deeper level lies the question of time itself. General relativity describes the unfolding of space and time as a fabric that can stretch, curve, and ripple. Yet, when traced back to the first instant, the equations collapse, delivering a singularity where the very notion of time loses meaning. Quantum cosmology attempts to resolve this paradox by marrying the uncertain, probabilistic world of quantum mechanics with the vast structure of relativity. In some interpretations, time does not begin but emerges, like frost crystallizing from vapor, or melody emerging from silence. If so, then asking whether a star is older than the universe may be the wrong question. Age presumes a single linear timeline, but the universe may be composed of multiple layers of temporal flow, stitched together in ways the human mind struggles to imagine. Evidence for such possibilities remains elusive, but hints flicker in the data. The cosmic microwave background, often called the afterglow of creation, has long been studied as the most ancient light in existence. Yet when mapped with exquisite precision, it reveals oddities. The infamous cold spot, a vast region of space with unusually low temperature, may be nothing more than a statistical fluke, or it may be a scar left by contact with another universe. Other subtle asymmetries challenge the assumption that the universe's birth was perfectly smooth. If these anomalies carry truth, then perhaps the microwave background is not only a relic of our beginning, but also a faint echo of cycles before. Some theories, like Penrose's conformal cyclic cosmology, suggest exactly this. In Penrose's vision, universes do not end with heat death, but fade into a state so uniform that it becomes indistinguishable from the conditions of the next beginning. In this endless procession, certain signatures, gravitational waves, perhaps even patterns in the microwave background, carry through. The possibility arises that stars themselves, or at least their building blocks, might span the divide, leaving behind the faintest of bridges from one cosmic epoch to another. If so, then the paradox of ancient stars is not an error but a message. The search for answers requires tools at the very edge of engineering. The James Webb Space Telescope has already revealed galaxies older and brighter than theory predicted. Structures arising a mere few 100 million years after the Big Bang. Its infrared gaze pierces the fog of early cosmic history, exposing suns that burn almost in defiance of time. On Earth, massive surveys collect the light of millions of stars, feeding it into spectrographs that unravel their chemical codes. From these codes, astronomers search for those few that whisper of near-pristine origins, hydrogen and helium, untainted by generations of fusion. Each candidate becomes another thread in the puzzle, another potential witness to an age before ages, and yet, for all the machinery and theory, the mystery remains. The stars that appear impossibly old do not vanish under scrutiny. They persist, steady and quiet, as though indifferent to the turmoil they provoke. The models are stretched, the numbers recalculated, yet the enigma holds. They shine not as answers, but as questions embodied in light. Questions that point toward something larger, deeper and stranger than the framework of current science. At the extreme edge of science, humility becomes the truest guide. These paradoxical stars remind humanity that the cosmos is not bound by the stories written so far. Whether shaped by dark matter, born in cycles of creation, or simply misunderstood by incomplete equations, they represent the boundary between knowledge and wonder. They are not just anomalies. They are doorways, luminous thresholds through which the universe invites inquiry into realities not yet imagined. From the perspective of modern astronomy, the mystery of stars that appear older than time is not a myth spun from imagination, but a riddle grounded in light and numbers. The mainstream view, cautious yet powerful, finds its footing in the physics of stellar birth and death, in the way matter itself evolves across cosmic epochs. It begins not with paradox, but with the first generation of stars, the legendary population 3. These stars, theorized, but never directly observed, were the universe's first fire. Forged in the wake of the Big Bang, they were built of almost nothing but hydrogen and helium, with scarcely a trace of heavier elements. Their size was extraordinary, many times the mass of the Sun, some perhaps 100 times larger. Such giants could not have lived long. Their lifetimes were measured not in billions, but in mere millions of years. They were the accelerants of cosmic evolution, their violent deaths scattering the first heavy elements across the primordial dark. Iron, carbon, oxygen, the materials that would one day compose planets, oceans, and the molecules of life, were born in their furnaces and cast outward in supernova of unimaginable force. If these titans were indeed so short-lived, then their light has long since faded. Yet their fingerprints remain. The stars that followed them, the so-called second generation, inherited the chemical ashes of their demise. These ultra-metal-poor stars, some still burning quietly in the Milky Way's halo, are like fossils embedded in the night. Their spectra, measured with modern instruments, show compositions almost untouched by time, hydrogen and helium in abundance, with only the faintest signatures of heavier elements. They are messengers from the dawn, not immortal suns, but survivors born in the immediate aftermath of creation. The process that gives rise to this gradual enrichment is known as stellar nucleosynthesis. Each star is a crucible where hydrogen is fused into helium, and helium into heavier elements through chains of nuclear reaction. When the most massive stars collapse and die, they scatter their enriched core into space. Each new cycle of birth draws from this expanding inventory, making the chemistry of stars richer with every generation. In this way, the metallicity of a star, its content of elements heavier than helium, becomes a clock, a measure of ancestry. Those with near-zero metallicity are the closest descendants of the firstborn. Astronomers have catalogued several such stars. SMSSJ 0313, discovered in 2014, contains less iron than 1 part in 10 billion compared to the Sun, the lowest ever recorded. Its existence suggests it formed from the remains of a single, massive population 3 star. He 1327, another, shows an equally extreme poverty of metals. These are not paradoxes, but relics, aligned with the models of cosmic evolution. They do not defy time. They testify to its earliest hours. Even the Methuselah star, HD 140, once thought to exceed the age of the universe, is today understood within this framework. Revised measurements of stellar opacities, distances, and nuclear reaction rates have brought its age into closer agreement with cosmology. Its light, rather than an error in the fabric of time, is a reminder that the boundaries of precision are always being refined. Yet these refinements extend beyond stars themselves. Cosmology, too, has adjusted its lens. The age of the universe, pegged at 13.8 billion years, comes from the expansion rate measured through the cosmic microwave background and the motions of galaxies. But these values are not absolute. They are derived from models that depend on constants and assumptions. Small changes in the Hubble constant or in the physics of early expansion ripple into the timeline. A tension remains between local measurements and those from the early universe, suggesting that something subtle may yet be missing. Still, these variations point to refinements, not ruptures, a tightening of the cosmic clock, not a rewriting of its existence. The remnants of ancient supernova further reinforce this story. By tracing the isotopic signatures they leave behind, scientists reconstruct the genealogy of the earliest stars. These supernova ghosts tell of cycles of birth, death, and rebirth, each enriching the universe for the generations to follow. The trail of evidence converges on a coherent vision that the oldest stars seen today are not older than the universe itself, but are its children born in its first breath in the mainstream view. Then, these stars are not paradoxes, but fossils. They are time capsules, carrying within their light the memory of creation's infancy. Their presence does not threaten the age of the universe. It affirms it. They are not older than time, but from its very dawn, living echoes of the first fire. The mainstream explanation rests not on overturning the laws of time, but on reading the subtle language written in starlight. Over the decades, the tools for this reading have sharpened. Modern spectroscopy allows astronomers to separate a star's light into its component wavelengths, revealing the elemental composition etched within. Each element imprints a unique signature, a fingerprint burned into the spectrum. For the oldest known stars, these spectra are astonishingly bare, showing little more than hydrogen and helium with only the faintest traces of other elements. To scientists, such scarcity is not confusion but confirmation. These stars formed before the universe was enriched by countless generations of supernova. One of the most compelling case studies is the star SMS SJO, found in 2014 using the SkyMapper telescope in Australia. It contains less iron than 1 part in 10 billion relative to the Sun. Such poverty of heavy elements is a clear sign of antiquity. This star likely formed from materials seeded by only one supernova, the explosive death of a massive population 3 ancestor. In its existence lies a direct clue to the earliest stellar generations, bridging a gap once thought unreachable. Other stars, like HE13 and HE01, tell similar stories. Their chemical compositions show unusual ratios of carbon, nitrogen, and oxygen, hinting at the particular physics of the supernova that preceded them. These peculiar signatures are like fossils of stellar deaths long vanished. Each pattern corresponds to models of how the first supernova expelled matter into the void, enriching it just enough for a new star to form. Large-scale surveys have multiplied these discoveries. The Sloan Digital Sky Survey, SDSS, the Hamburg ESO Survey, and more recently Gaia, have mapped vast swaths of the sky, measuring the properties of millions of stars. Out of these immense catalogues, astronomers pluck out the rarest, those with the lowest metal. These are precious needles in a cosmic haystack, but each one is a relic, a surviving witness of the first chapters of the universe. Gaia, in particular, with its exquisite measurements of stellar positions and motions, has revealed that many of these ancient stars belong to the Milky Way's halo, a diffuse, ghostly structure surrounding the familiar spiral disk. The halo itself is a kind of graveyard of early stars, built from smaller galaxies that merged into our own. Its contents preserve a record of ancient times, fossilized in starlight. The James Webb Space Telescope extends this quest even further. Its infrared eyes are tuned not only to stars within our galaxy, but to galaxies from the dawn of time itself. Already it has detected galaxies that existed only a few 100 million years after the Big Bang, some showing surprising brightness and complexity. These findings push models of early star formation to their limits. Within such primordial galaxies, astronomers hope to catch the faint, collective glow of population 3 stars, not individually resolved, but in their combined fingerprints. If Webb succeeds, it would provide the first direct evidence of the very first generation. No longer a matter of theory alone, the mainstream perspective does not dismiss paradox, but seeks to resolve it with refinement. Take the Methuselah star, HD 140,000, 283, once thought to be older than the universe itself. Early calculations placed its age at around 14.5 billion years, slightly older than the 13.8 billion year universe. Yet with improved parallax measurements from the Hubble Space Telescope and refined nuclear reaction rates, the estimate fell closer to 13.7 billion, still ancient but consistent with the cosmic timeline. The paradox dissolved, not because the star grew younger, but because human understanding sharpened. This process reflects the nature of science itself. Apparent contradictions drive refinement, and mysteries are narrowed until they reveal the truth. Another refinement arises from cosmology. The exact age of the universe depends on the Hubble constant, the rate of cosmic expansion. Two different methods of measuring it produce slightly different results, a tension that has not yet been resolved. One method, based on the cosmic microwave background, points to a slightly slower expansion and thus an older universe. Another, based on nearby supernova and Clifford variables, suggests a faster expansion and a younger universe. The difference amounts to hundreds of millions of years, enough to shift the apparent relationship between stellar ages and cosmic age. Mainstream cosmology interprets this not as a breakdown of the timeline, but as a challenge to refine models of expansion, dark energy, and the early universe. The story of stellar ancestry also finds depth in supernova remnants. When a star dies in a violent explosion, the cloud of debris expands and cools, but its chemical composition remains. Astronomers analyze these remnants, comparing them with the abundances seen in ancient stars. The match is striking. The peculiar chemical patterns of metal-poor stars align with simulations of supernova yields from massive, early stars. In this way, the debris of ancient deaths is linked directly to the birth of the survivors still burning today. Mainstream theories converge on a clear interpretation. No star is older than time itself. Instead, the oldest known stars are fossils of the universe's youth, forged in the immediate aftermath of the Big Bang. They are not paradoxes, but archives, preserving in their atmospheres the chemical memory of the first supernova. Their light does not contradict cosmology, but complements it, showing how the raw hydrogen and helium of the early cosmos became the diverse periodic table we know today. And yet, this perspective does not diminish their wonder. To call them fossils is not to strip them of mystery, but to elevate them. For in fossils lies history, in fossils lies survival. These stars are survivors of creation's dawn, still glowing after nearly 14 billion years. They are older than the Earth, older than the Sun, older than the galaxy's familiar spiral arms. They were already ancient when the Milky Way itself was young. In this mainstream view, the universe remains coherent, but the stars themselves remain profound. Their light is not a riddle that shatters the framework of time, but a window into its earliest unfolding. They are not older than the cosmos, but as old as its first song. The search for meaning in the oldest stars does not end with the cautious boundaries of mainstream astrophysics. Beyond the rigor of accepted models lies a realm of speculation, daring, fragile, yet irresistible. For when data brushes against the edges of comprehension, imagination often steps in to fill the silence. Some scientists, philosophers, and dreamers have proposed that the faint glow of ancient stars may be more than just remnants of the first generation. They may be whispers of something far stranger, relics of a universe that did not begin as the Big Bang, but as something older, cyclical, or infinite. One speculative idea arises from cyclic cosmologies. In these visions, the universe does not begin once and end once, but oscillates endlessly. A cosmos expands, collapses, and is reborn, like a chest rising and falling with eternal breath. Each cycle erases most traces of the one before, yet perhaps not all. Some theories suggest that information, or even physical structures, might survive a cosmic rebirth. Could stars themselves persist across such transitions? To conventional physics, this seems unlikely, for a collapse into a singularity would compress all matter beyond recognition. Yet in speculative models, where the universe bounces rather than ends, where contraction leads smoothly into new expansion, fragments of matter might carry through. If so, a handful of stars glowing today may not be children of this universe's dawn, but orphans of an earlier cycle. Other hypotheses turn to the idea of pre-Big Bang matter. According to these, the Big Bang was not the ultimate beginning but a phase transition, a violent reshaping of conditions that already existed. If so, then some of the matter from before could have slipped into the expanding fabric of our cosmos. If that matter condensed into stars, those stars would appear inexplicably ancient, out of joint with our timeline. The idea remains speculative, yet when astronomers measure stars that appear nearly as old as the universe itself, it offers a poetic way of explaining the paradox. The concept of the multiverse adds another layer of speculation. In the inflationary model of cosmology, the universe we see may be only one bubble in a far larger cosmic foam. Each bubble has its own physics, its own constants, its own unfolding. What if, in some way unknown, stars from another bubble found their way into ours? Perhaps through quantum bridges, wormholes, or the imperfect stitching of boundaries between universes. These stars would seem older, stranger, perhaps chemically unlike their neighbors, as though visitors from another cosmic homeland. Mainstream science does not embrace this view, but the allure remains strong, for it would explain anomalies not by bending time but by expanding space into realms beyond. Imagining quantum gravity theories add further mystery. In attempts to reconcile relativity with quantum mechanics, time itself becomes malleable, uncertain, perhaps even illusory. Some models suggest that time could loop, branch, or emerge only after certain conditions are met. In such frameworks, before the Big Bang may not be a nonsensical phrase, but a clue that the boundaries of time are less rigid than they seem. If time is cyclic or fractal, then stars we call ancient could in fact be witnesses of epochs prior to ours. Carried forward across hidden folds of cosmic chronology, Stephen Hawking's No Boundary proposal adds a poetic layer to these speculations. In his vision, the universe has no sharp beginning, no singular edge where time bursts into being. Instead, time curves smoothly, like the surface of the earth, with no clear boundary to mark a start. If that is true, then the oldest stars are not paradoxes at all, but natural outgrowths of a cosmos that never needed a first moment. They are not intrusions from before time, but luminous confirmations that time itself is less absolute than we assume. And so, in the speculative imagination, these stars become more than fossils of creation's dawn. They become fossils of eternity, hints of an infinite cosmos that has no beginning and no end. Their faint light becomes not only a scientific puzzle, but a philosophical challenge, beckoning humanity to reconsider its own story. For if the stars are older than time, then perhaps time itself is not a river with a source and a mouth, but an ocean without shore, where existence has always been and will always be. The fringe theories may never find confirmation. They may remain in the realm of thought experiments, poetic gestures toward the infinite. Yet they remind us that science is not only a discipline of evidence, but also a dance with imagination. In the glow of these two ancient stars, perhaps both are necessary, the precision of measurement, and the daring to wonder whether what burns in the abyss is not only old, but eternal. Speculative thought has always walked in the shadow of observation, daring to reach where data cannot yet travel. When astronomers gaze at stars that defy expectation, they do not only sharpen their instruments, they also allow imagination to stretch beyond the limits of the known. The mystery of ancient stars, with their paradoxical ages and near-pristine compositions, becomes a canvas upon which entire cosmological philosophies are painted. Among the most evocative is Roger Penrose's conformal cyclic cosmology. In this vision, the universe is not a singular story with a beginning and an end, but an endless chain of eons. Each eon begins with a big bang and ends in a long, quiet fading, where black holes evaporate and all matter drifts apart until nothing remains but radiation. At that point, scale itself loses meaning. The cold emptiness of one eon transforms seamlessly into the hot density of the next. No boundary, no singularity, only the smooth handoff from death to birth. Within such a picture, the idea of before and after dissolves. The faint glow of today's stars could carry whispers not just from our universe's dawn, but from the ashes of an eon that lived before. Penrose even proposed that imprints of past eons might be encoded in the cosmic microwave background, tiny circles of unusual smoothness marking where black holes from a former universe may have left their scars. If light can remember across eons, perhaps matter can too. Loop quantum cosmology offers another radical alternative. In this theory, the singularity of the Big Bang is avoided because space and time themselves are quantized, built from discrete units, smaller than any particle. Instead of an infinite compression into nothing, the universe contracts to a minimum size and then bounces outward again. Time does not end at the bounce. It extends through. What we call the Big Bang becomes a big bounce, a pivot between contraction and expansion. In such a framework, remnants from a previous cosmic phase might endure into hours. If even a handful of stars or protostructures survived that passage, their existence today would not be a contradiction but a revelation, a sign that universes recycle themselves, and that survival is written into the fabric of reality. Eternal inflation carries speculation in a different direction. According to this model, space itself expands eternally, with local regions, bubbles slowing enough to form universes like ours. Each bubble can carry different physical laws, different constants, different stories. If this cosmic foam is truly infinite, then our universe is one among countless others, each with its own stars and galaxies. But what if the boundaries between bubbles are not impermeable? Some theories allow for collisions or quantum tunneling between them. If so, could a star wander across the divide, carrying into our sky the chemistry of another cosmos? Its light would puzzle astronomers, not because it is older than our universe, but because it is not of our universe at all. The speculative landscape also entertains visions where time is not linear but layered. Quantum mechanics allows for the possibility of branching paths where histories split and coexist in superposition. If cosmic history itself branches, then some stars could belong to slightly different versions of the early universe, versions that have somehow bled into ours. Their paradoxical ages would be artifacts of this overlap, cosmic ghosts shining into a timeline not entirely their own. Stephen Hawking's no boundary proposal, too, remains a poetic anchor in these speculations. In his mathematical framework, the universe does not have a sharp origin. Rather, Time curves smoothly like the surface of a sphere. Asking what came before the Big Bang becomes like asking what lies north of the North Pole. In such a universe, the oldest stars need no explanation beyond their persistence. They are not relics from before time. They are natural growths within a cosmos that never had a clean beginning. Their existence is less a paradox than a reminder that human language, with its hunger for starts and stops, may not capture the fluidity of cosmic reality. Some of the most imaginative theories propose that these ancient stars could be made not only of ordinary matter, but also of something more exotic. Stars powered partly by dark matter, so-called dark stars, could burn for extraordinary spans, far longer than nuclear fusion alone would allow. If such objects exist, they might preserve signatures of earlier universes or earlier phases of this one, their light carrying a history hidden from ordinary observation. These are speculative, but they offer a way of reconciling impossible longevity with new physics, hinting that the paradox of age might be solved not by rewriting cosmology, but by expanding the catalogue of stellar possibilities. Speculative cosmology often blurs into philosophy. Ancient cultures imagined eternal cycles. The Hindus spoke of kalpas, great ages of creation and destruction. The Stoics envisioned a cosmos reborn in fire. Norse mythology told of Ragnarok, followed by renewal. These mythic echoes resonate with the scientific visions of cyclic universes and bouncing cosmologies. They suggest that humanity has long sensed the possibility of an eternal rhythm, where creation is not singular but ongoing. In that light, the oldest stars become more than astrophysical puzzles. They become archetypes, connecting modern physics with ancient intuition. In the poetic imagination, the paradoxical stars transform into fossils of eternity. Their survival becomes a message, not only about the physics of nucleosynthesis or cosmic expansion, but about existence itself. If time loops, if universes cycle, if matter and light can cross boundaries that seem absolute, then perhaps nothing is truly lost. Perhaps the stars remind us that the cosmos is not a story with a prologue and an epilogue, but an infinite song echoing across eons without beginning or end. Speculation may never find the evidence it seeks. Cyclic models, multiverse hypotheses, quantum bounces, all may remain elegant ideas without direct confirmation. Yet their value lies not only in their truth, but in their challenge. They force science to consider what might lie beyond the measurable, and they invite philosophy to dance once more with the stars. The light of two ancient suns, shimmering against the darkness, becomes a mirror in which humanity sees not only the cosmos, but its own longing for permanence, its refusal to accept a finite story in the end. The speculative theories remind us that mystery itself is a necessary part of science. Without it, knowledge would stagnate. With it, the cosmos remains alive, not a solved equation, but an endless horizon. And in that horizon, the faintest of stars may shine with the weight of eternity. The hunt for the universe's oldest light continues, not in myth or speculation, but in the quiet hum of machines and the restless patience of astronomers. Across deserts, mountain tops, and the frozen silence of space, instruments now sharpen their gaze to pursue the first stars, the elusive population 3 stars, born from pure hydrogen and helium, untouched by heavier elements. They are the hypothetical architects of cosmic dawn, their lives too short and too brilliant to endure, their deaths seeding the cosmos with the metals needed for all that followed. Yet despite decades of searching, not a single one has been seen directly. The James Webb Space Telescope, suspended at the Lagrange point like a golden eye staring into eternity, has made this quest its defining ambition. With every deep field image it captures, astronomers comb through galaxies that glimmer from more than 13 billion years ago, searching for spectral fingerprints that betray the presence of stars older than galaxies themselves. Alongside Webb, an armada of instruments carries the pursuit further. The Gaia mission, mapping over 1 billion stars in the Milky Way with unparalleled precision, charts their motions like dancers frozen in cosmic choreography. By tracing the arcs of their journeys and measuring their faint chemical signatures, Gaia helps identify the rare survivors from the galaxy's earliest epoch. These stellar relics, poor in metals but rich in time, serve as breadcrumbs leading back to the first chapters of creation. Advances in nuclear physics refine the art of stellar archaeology through careful modeling of fusion chains and isotope abundances. Scientists calibrate the clocks buried in stellar hearts. Uranium and thorium isotopes, decaying at rates measured over billions of years, become cosmic chronometers, whispering the ages of stars with margins of error that grow smaller each decade. Each refinement narrows the gulf between speculation and certainty, yet also deepens the strangeness of stars whose ages press uncomfortably against the accepted age of the universe itself. On Earth, supercomputers stage vast digital experiments, simulating the first billion years after the Big Bang. Within these calculations, entire galaxies emerge from dark matter scaffolding, stars ignite in primordial gas clouds, and black holes carve their influence into the fabric of young universes. These simulations offer testable predictions: the brightness of a population 3 cluster, the chemical signature of its supernova, the faint patterns their remnants would leave in the intergalactic medium. Observers then turn telescopes skyward, searching for reality's echo of the models, bridging imagination with observation. None of this unfolds in isolation. Modern astronomy thrives as a global endeavor. Observatories in Chile, Hawaii, Spain, and the Antarctic ice feed data into shared repositories. Teams numbering in the thousands, speaking dozens of languages, contribute fragments of a single puzzle. Each night's observation is checked, shared, debated, and folded into a story larger than any one person or nation. The search for the first stars has become one of the most international pursuits in human history, a reminder that some mysteries are too vast to be solved alone. Yet, for all these efforts, the answers remain incomplete. Webb peers deeper, Gaia maps with finer precision, physicists refine their models, and still the stars of first light elude direct capture. Each discovery seems to widen the mystery rather than close it. A galaxy too massive, too early. A star older than the framework allows. Light that should not exist, and yet does. The universe continues to resist final explanation, as though guarding its origins with deliberate silence. And so the pursuit endures. Telescopes planned for the coming decades, the extremely large telescope in Chile, the square-kilometre array in South Africa and Australia, promise sharper visions and deeper listening. But even as technology advances, the essence of the quest remains unchanged, a human longing to see the beginning written in the sky. The mystery does not diminish with knowledge, it grows. Each step forward reveals new depths, each answer breeds questions more profound than before. In chasing the oldest starlight, humanity confronts not only the universe's beginnings, but its own place within a story that may have no end. The search for the first stars is as much about silence as it is about discovery. Between each spectrum recorded, each faint photon caught by a detector, lies the awareness that the universe holds its secrets tightly. The James Webb Space Telescope, whose mirrors gleam like folded wings of gold, was not designed merely to look far, but to look back. With its infrared gaze, it pierces the veils of time, uncovering galaxies that formed when the cosmos was less than 200 million years old. Within these embryonic structures, astronomers hope to glimpse the fingerprints of population 3 stars, the giants that once burned with impossible brightness, fusing hydrogen and helium into the first atoms of carbon, oxygen and iron. Yet Webb does not hand over answers. Its deep field images dazzle with swarms of galaxies, each one a mosaic of countless suns. But disentangling those that belong to the earliest stellar generations demands patience, precision, and theoretical courage. Spectral analysis becomes the astronomer's scalpel, slicing through light to uncover hidden chemistry. The absence of metals, the faint curve of energy peaks, the disproportionate brightness of ultraviolet radiation. These are the subtle clues that whisper of primordial stars. It is like hunting ghosts, tracing presences that reveal themselves only in the faintest distortions of ancient light. Meanwhile, Gaia continues its quiet revolution closer to home. While Webb gazes outward, Gaia looks inward, mapping the Milky Way with a fidelity no civilization has achieved before. Over 1 billion stars are pinned to its charts, their distances, velocities, and motions recorded with millisecond precision. It is in these motions that hidden histories are revealed. Some stars orbit the galaxy with strange eccentricity, plunging through the halo and drifting back again. Remnants of cannibalized dwarf galaxies absorbed billions of years ago. Others reveal themselves through their elemental simplicity. Stars, almost devoid of metals, time capsules from an epoch when the universe had only just begun to forge complexity. Among these are the ultra-metal-poor stars, fossils of the second generation, children of population 3 supernova. Each one is a survivor that outlived empires of stars brighter and faster burning than itself, bearing chemical scars of explosions that ended long before the Earth was born. But even these survivors are only shadows of the true first stars. The giants themselves are thought to have lived only a few million years before collapsing into black holes or erupting as No telescope will ever see them alive. Instead, astronomers seek the faint imprints they left on their surroundings, altered chemical ratios in ancient clouds, unexpected brightness in young galaxies, patterns written into the cosmic microwave background itself. It is like trying to reconstruct the life of a vanished species from footprints. Fossilized in stone, nuclear physics sharpens these reconstructions. Laboratories on Earth mimic the interiors of stars, smashing nuclei together under extreme temperatures and pressures to refine the models of fusion. These experiments allow researchers to calculate more precisely how long different isotopes can survive in stellar cores and in interstellar space. Radioactive chronometers, uranium-238, thorium-232, decay on timescales of billions of years, their ratios serving as cosmic clocks. By measuring them in ancient stars, astronomers attempt to determine not just relative ages, but absolute lifespans. The uncertainties remain, but each improvement tightens the grip on the truth, forcing models of stellar evolution and cosmic expansion to reconcile with what the clocks insist. Parallel to this, supercomputers summon entire universes within their circuits. They take equations of fluid dynamics, thermodynamics, quantum fields, and gravity, and let them evolve from the first fractions of a second after the Big Bang. Out of mathematics emerge filaments of dark matter, rivers of gas falling along invisible scaffolds, and galaxies condensing in knots of gravity. Within these galaxies, stars ignite, first in chaos, then in patterns that resemble the galaxies seen by Webb. The simulations allow astronomers to test what kinds of population 3 clusters might survive long enough to leave traces today, and how their deaths seeded the cosmos. They reveal possibilities that observations alone cannot. Faint starburst, unstable gas clouds collapsing under the influence of dark matter, supernova so powerful that they cleared entire proto-galaxies of gas, halting star formation for eons and always. These theoretical visions must be checked against the sky. Observatories on Earth play their part. The Subaru telescope in Hawaii, the Very Large Telescope in Chile, and other instruments carry out massive spectroscopic surveys, searching for stars in the Milky Way halo with chemical patterns matching ancient predictions. Each survey adds thousands of candidates, and among them, a few emerge as extraordinary stars with metallicities 100,000 times lower than the Sun's, preserving a chemistry that feels like the echo of the universe's first breath. International collaboration binds all these threads. Data flows between continents, stored in vast archives open to scientists worldwide. Teams of researchers, sometimes numbering in the thousands, work together across time zones, combining telescope data, nuclear models, and simulations. In this global mosaic, no single discovery belongs to one person or one nation. Each fragment only gains meaning when set beside the others. The mystery of the first stars has become one of the most unifying endeavors of science, a collective act of reaching backward through time. And yet, the closer science approaches, the more enigmatic the picture becomes. A galaxy too bright, too early. A star whose age estimate presses against the boundaries of cosmology. Chemical abundances that do not match predictions. Each breakthrough raises questions sharper than those it resolves, as though the cosmos continually reshapes its mysteries the moment they seem within reach. The present effort, though immense, is acknowledged as only a beginning. On the horizon rise telescopes even larger, their mirrors spanning tens of meters, capable of dissecting the faintest galaxies with unprecedented clarity. Radio arrays stretching across continents prepare to map the neutral hydrogen of the early universe, tracing the cosmic dawn not in starlight but in the whisper of atoms aligning their spins. And still further ahead, physicists and cosmologists dream of detectors that might sense gravitational waves from the first stars collapsing into black holes, ripples in space-time, themselves carrying the signatures of creation. The pursuit is relentless, not because the answers promise closure, but because the mystery deepens with each step. To find the first stars is not merely to learn what they were, but to confront what it means for anything to begin. Each photon caught, each simulation rendered, is part of a dialogue with the cosmos itself, a conversation humanity has only just begun, and one whose final words may never be spoken. The stars have always carried more than light. They have carried meaning. Across deserts and oceans, temples and towers, human eyes have lifted upward, searching not only for direction but for origin. In the distant glow of the heavens, ancient peoples inscribed myths, seeing gods, heroes, and the shapes of their fears written in constellations. The stars became the first mirrors, reflecting the question that has haunted every age. Where did it all begin? Now, armed with instruments of glass and gold, the question has not changed, only deepened. The search for the first stars is not merely a scientific pursuit. It is a continuation of that ancient hunger for beginnings. To glimpse them is to touch the threshold of time itself, to stand at the doorway of creation and wonder whether what lies beyond is knowable or forever hidden. Stars have always appeared eternal to human perception. They rise and set across countless lifetimes, outlasting kings and empires, religions and revolutions. The pyramids have crumbled, the voices of philosophers have faded, but the same constellations burn as they did in the eyes of those who first named them. To learn that stars too are mortal, that they are born, live, and die, is to confront a truth more humbling than any myth. Yet some stars, the rarest and oldest, stretch this mortality toward eternity, defying the brief span of humanity. They become emblems of permanence, anchors in a universe where even galaxies drift apart. And here lies the paradox. The search for the first stars draws humanity toward the concept of before time, yet human minds are creatures of time, sculpted by rhythms of heartbeat, sunrise, and season. Thought itself is bound to sequence, past, present, future. To imagine a star older than the universe is to collide with the limits of language, to attempt to measure silence with sound. Philosophy has long circled this enigma, asking whether the human mind seeks eternity not because it can grasp it, but because it fears impermanence. Perhaps in these stars humanity is not finding cosmic beginnings, but projecting its longing for what does not end. Still, science persists with humility. Each observation, each theory, is less a conquest of truth than a surrender to wonder. The pursuit reshapes those who undertake it, teaching patience, reverence, and the courage to accept uncertainty. Whether the first stars are ever truly found may matter less than the journey itself. The act of turning human curiosity outward into a universe vast enough to absorb it. In the end, the image lingers, two stars, impossibly ancient, glowing in silence at the edge of time. Survivors of a forgotten dawn, they whisper not of endings, but of continuities. Creation, they suggest, is never a completed act. It is a river, flowing through epochs and minds, carrying forward the mystery of existence. And in their faint, unyielding light, the story of beginnings does not close, but begins again. The longing for origins is woven into the marrow of human existence. Every culture, every epoch, has returned to the question in one form or another. What was the first light? What stirred before the world began? From the hymns of the Rig Veda to the silence of Buddhist cosmologies. From the Genesis proclamation of "Let there be light" to the cyclical fires of the Maya, humanity has always felt the need to frame beginnings within stories. Stars became the natural stage upon which these stories unfolded. Their patient glow suggested a permanence that life on Earth could never offer, yet permanence itself is an illusion. Science revealed that stars are engines of impermanence, burning, transforming, collapsing, dispersing. But in their destruction they sow renewal, scattering heavy elements that form new stars, new planets, new possibilities for life. This cycle of creation and decay speaks to something profoundly human, the sense that endings are not truly ends, but transformations. And when astronomers discover stars whose ages brush against the universe's own, it becomes difficult to know whether to treat them as relics or as prophecies, not frozen remnants, but living proof that the cosmos itself is still unfolding. The paradox of stars older than the universe unsettles more than physics. It unsettles philosophy. If time is the stage upon which all events occur, how can anything stand before its curtain has lifted? Augustine wrestled with this very paradox more than 15 centuries ago. When asked what God was doing before creation, he replied that time itself was made with the heavens and the earth. There was no before, only the timelessness in which time itself emerged. Modern cosmology echoes this riddle. The Big Bang is not an explosion in time, but the birth of time itself. Yet here are stars whose chemistry hints at ages that seem to precede the script. Are they mistakes of measurement or messages written in contradictions? Such questions bleed into the realm of metaphysics. To search for origins is to acknowledge the fragility of the present. If the universe has a beginning, then it too has an end. And all of human striving, every art, every empire, every memory, is a brief flicker in a cosmic span. The discovery of stars that seem to carry echoes of an earlier creation offers another possibility, that beginnings and endings are not as final as they appear. Perhaps the universe is not a line drawn from birth to death, but a circle, a rhythm, a breathing in and out across eternity. In that vision, these stars are not anomalies, but witnesses. Their endurance a reminder that creation is never truly closed. For scientists, this pursuit carries a humbling irony. The most advanced telescopes, the most intricate models, are deployed not to reveal the distant future, but to peer into a past that may have no boundary. The James Webb Space Telescope, poised beyond the atmosphere in the darkness of Lagrange Point 2, is less a machine of sight than a time machine, pulling back the veil on galaxies older than imagination. Yet even its infrared eyes may never resolve the true first stars. What it can give, instead, is a sense of nearness, of brushing against the fabric of the unknown, of feeling the edges of comprehension tremble. For the human heart, however, the search means more. It means that humanity has not abandoned wonder. In an age where technology moves faster than wisdom, where screens glow brighter than the night sky, the decision to build billion-dollar observatories to search for two ancient stars speaks of something timeless. It speaks of the same impulse that drove ancient poets to tell stories of beginnings, the same impulse that carved observatories into stone long before telescopes existed. The search is not only for stars, but for place, for assurance that humanity belongs to something greater than itself. And in this, the stars return the gaze. They do not answer with clarity, but with persistence. Their light, stretched across billions of years, falls quietly into human instruments, into human eyes. It carries neither confirmation nor denial, only the reminder that existence itself is vast enough to sustain mystery. Whether they are fossils of eternity, survivors of an earlier creation, or simply misread in their age, they have already achieved something profound. They have reshaped the way humanity conceives of itself, because in the silence of the night sky, the paradox remains. To seek the first stars is to seek the moment when darkness became light, when nothing became something. Yet perhaps the lesson is not to find a singular moment, but to recognize that creation is ongoing, eternal, unfolding not only in the depths of the cosmos, but in every act of curiosity, in every spark of human thought. And so the image lingers, as it did in the opening vision, two stars glowing in the abyss, survivors of a forgotten dawn. They do not promise answers, only endurance. They whisper that creation is not a moment in the past, but a movement without end. Humanity, in searching for them, discovers not only the story of the universe, but the story of its own longing, a longing that does not fade, but burns like starlight across the ages.